Welcome back to the ChemDoctor. This video and the videos that follow it have to do with what's called Le Chatelier's principle. And Le Chatelier's principle has to do with a phenomenon that occurs with chemical reactions that are at equilibrium. And when you have a chemical reaction that is at equilibrium, you can alter the position of that equilibrium by changing the concentration of the reactants or the products, or all the above. You can alter the equilibrium position by manipulating one of the gaseous components by changing its pressure due to a volume change in the container, and or you may also manipulate the temperature of a reaction and alter its equilibrium position. And Le Chatelier's principle is a set of principles that allows us to predict what's going to happen, which direction a reaction is going to shift in order to reattain equilibrium when we manipulate one of the three category areas that I just mentioned. So the idea here is that you've got a chemical reaction that is at equilibrium, and then you do something to it. All right, and there are three main categories of ways in which we can alter the position of a reaction so that that reaction then has to respond to the disturbance by shifting back to equilibrium. All right, the first way that we can knock a reaction out of equilibrium is by manipulating the concentration of reactants, products, or all the above. We've already dealt with this area, although I didn't call it Le Chatelier's principle. We've already learned about the reaction quotient Q, and when we set up a chemical reaction with initial concentrations of the reactants and the products, we calculate Q in order to figure out which way the reaction has to shift to get back to equilibrium. And once we know Q, then we can set up our ICE table, or we can set up our box, and we can solve for the new equilibrium concentrations. A second way that we can knock a reaction out of equilibrium is by manipulating the pressure of one or more components of the reaction that are gaseous. So pressure of gaseous equilibrium components. And the way that we manipulate the pressure is by volume change. And I'll get to that, or to this issue, after we deal with category number one. And then finally, the third area that we're going to talk about in subsequent videos is by manipulating the temperature of a reaction. All right, an equilibrium position occurs at a fixed temperature. So if we change the temperature of a reaction that is at equilibrium, that means that that reaction is going to shift to a new equilibrium position that will be at the new fixed temperature. All right, now let's start by talking about area number one. Even though we've already talked about reaction quotient Q, what I want to do here is talk about the effect of concentration on equilibrium in a more general way. A lot of times you can predict which way a reaction is going to go when you change the concentration of one of the reactants or products that are in the equilibrium position. So let's look at a simple reaction here, the conversion of N2O4 to two NO2s. The Kc for this reaction is equal to 5.9 times 10 to the minus third. This is a small equilibrium constant by my definition, and in previous videos what I defined as small was any equilibrium constant that was 1 times 10 to the minus third or smaller. So this Kc is small. Now we can represent the equilibrium position of this reaction by drawing a seesaw, like a seesaw you would find in a playground. And the seesaw that I draw here is going to be at an angle like this, where it is favoring the reactant. So I'll put my N2O4 on this end and my two NO2s up here on this end. And why am I drawing it this way? Because you need to pay attention to your equilibrium constant. You see that it's a small number. What this tells us is that the reactants at equilibrium for this particular reaction are at a higher concentration than the products, which is the reason why the equilibrium constant is a small number, because we're dividing a small product concentration by a large reactant concentration, which ultimately gives us a small equilibrium constant. So we can draw our seesaw like this. You can imagine a large amount of reactant sitting on the seesaw and a smaller amount of product sitting on this side. So the seesaw is slanted down to the left. A perfectly equivalent type of seesaw situation where the mixture of reactants and products is more equivalent would look like this, where the seesaw itself is essentially flat going across here. And that's not the situation that we have with this particular chemical reaction, because again, to emphasize, the equilibrium constant is small for this. So let's say that we were to add some NO2 to the reaction mixture, which is already at equilibrium, and draw a new seesaw to represent that. So you can imagine that if we added more material here, NO2s to this end of my seesaw, it's going to flatten the thing out, right? Because we're adding weight essentially to the other side, to the light side of my seesaw. So the seesaw is going to be pushed down, all right? So that we end up with a configuration which is out of equilibrium. Now let me do my arrow this way. So this thing is more flattened out. So now the question is, how do we get back? How do we get back to the situation that we have here? Because this is the equilibrium. This is the equilibrium position for this reaction. Well, the only way that that can happen is if some of the NO2 is converted to N2O4. So in other words, the reaction is going to have to shift to the left. All right, the reaction is going to have to shift to the left in order for us to get back to this situation here, where the seesaw is once again leaning down on the left side and pointing up on the right side. So if we had been looking at this reaction in the previous videos where we calculated a Q, all right, the scenario that we have here suggests that Q is greater than K, all right, and reaction will shift left. Keep in mind that the reason I am drawing the seesaw this way is because the equilibrium position of this reaction at whatever fixed temperature we're at favors the reactants. So the seesaw is going to be heavy on the left side. Okay, now, by the same token, if we were to look at another scenario here where the seesaw was at a more acute angle than our equilibrium position. So this thing is jammed right down on the ground, all right? Now, that's a situation where the reactant concentration, so this is non-equilibrium. Let me just write that here so no one can get confused. So now we have a reactant situation, all right, which is far, far greater than the products, but beyond the position of equilibrium. This is beyond the equilibrium position. So if you remember back into the previous few videos, this is a situation where Q is actually less than K. So the reaction is going to have to shift. It's going to have to shift right to get back to equilibrium, all right, to get back to this position where the seahorse, once again, has that more acute angle, right, but the angle which is proper for the equilibrium position. So this is my equilibrium seesaw, all right, my equilibrium seesaw, where K is 5.9 times 10 to the minus third. So in this position here, the reaction had to convert some N2O4 into NO2s in order for the seesaw to balance out again to its prescribed location, right, based on what the Kc is. So you can estimate, when you look at a chemical reaction, which way the reaction is going to shift very easily with no calculations when either the reactants are being added to the equilibrium position or products are being added to the equilibrium position. Whichever one you're doing, you're going to have to shift away from that added pressure. In situations where the problem dictates that you've got the addition of both reactants and products at the same time, then what you're going to have to do is go in and calculate your Q value and compare it back to your K in order for you to predict which way the reaction's going to shift. And with that, I'm going to go ahead and close this video.